Okay. Good morning, everybody. I hope everyone's having a wonderful day. So, I want to pick up from where I was last day. So, I must stress that in this course, you'll see a whole bunch of different abstract data types. I'm just giving us a basic introduction of the idea, but we'll be exposed to this idea throughout the term. So, we'll be seeing lots and lots of examples of abstract data types. I described this idea of a stack last time just to illustrate this concept. And keep in mind that we will more thoroughly study stacks later on in the term. I just want to give you an example of an abstract data type. And remember, the big thing about an abstract data type is it specifies the what, like what it is. So it's not saying how it does things, it just says what it is. It's a specification. So, for example, with the stack, I have, say, these two operations. There's other ones I could also define for a stack, but these are two that are of primary interest for us here today. I have this one called push, where it takes in an element as input, and it will place this element on the top of the stack. Pop will remove and return the top element from the stack, and null. And I must stress that oftentimes in this course, just because I like to encourage you to think about this not just in one language, but a concept that can be easily applied to many other languages. Sometimes you'll find that when I use the word null, what I refer to is null pointer, something like in C++. Sometimes I also use the word nil as well. These are all the same thing. So if you ever find me using any of these three terms, they're all the same thing as far as we're concerned in this course. Different programming languages will call null different things. Some call null pointer, some call it nil, some call it null. But anyways, we had this idea where we think of it like a stack of plates, right? Or I can put, so for example, I can have a stack here. I can push this element onto the stack, but it goes always onto the top of the stack, right? So if I push this blue plate, the blue plate goes on the top of the stack. Likewise, if I push this grayish plate, I could push that on. When I do a push operation with this plate, it goes on the top of the stack. If I pop, it's always off the top of the stack. One thing that you'll notice very quickly about that makes the stack rather interesting is it's always relevant to what's on the top of the stack. Not really so much the stuff that's at the bottom of the stack. So there's different data, you can think of these different data types, these abstract data types, as ways of representing different types of data, and these data have different functional purposes. So when we get to studying stacks, you'll see what I mean, why a stack might be useful if you think of it more computationally. But the stack analogy works well enough for us for this example. So first, does everybody understand these two operations? So it's just, I put something on the top of the stack, pop will remove and return it. If I have no plates in my stack, then I return null. So give me 2 thumbs up if we're all good so far. Just give me 2 thumbs up. Awesome, awesome. So I give you a few examples here. So for example, if I have this stack S, A here is at the top, so whatever A is, this is the element that is on the top of the stack. So if I do a pop, I would get back A here. So if I do my pop, I get A, but if I push F, F goes on the top of the stack. So what I've described to you is just a what, right? I didn't tell you how exactly this is done, right? But we're very used to this idea, especially for previous courses where we actually have like a representation and we try to program it, right? Very often. Now, remember that the ADT describes the type of data stored and the operations, not how it does it. Just like my analogy with the car. So you know how I told you how we could get into a car. The car has all sorts of functions that it's capable of. I can push on the gas pedal, I can turn on the radio, heck, I can even change the tires. All of these are things that the car can do, right? Functionally speaking. Now, I don't necessarily know what happens with the car and its internals. The thing is, if you follow me carefully here, if I have one of these abstract data types like my stack, the idea is very simple. The abstract data type tells me what it is, but the thing is if ever I implement the abstract data type, then I could call it that thing. So for example, if I were to implement the stack, then I could call whatever my implementation is a stack. So if we could implement the ADT, which is a data structure, then we could call that implementation one. So in this case, if I were to implement the abstract data type, then I could say, now I'm a stack too. Now, there's something very interesting here. This should remind you of something that you may have seen in 115. There's a very interesting object-oriented feature that you may have seen in C++ that sounds a lot like this. Does anybody have any ideas of what I might be alluding to? So not just methods, not methods or member functions. I'm referring to something, a specific object-oriented feature, and we gave a hint that the abstract data type has a very natural representation as a class. I'll give you a hint. It starts with an I. So if I have one class, and remember I told you last day, yeah, okay, technically it's an interface. The ADT is an interface, most certainly. But what is the feature in something like C++ I could use to implement all of the features for my so-called abstract class? So inheritance, that's what I'm referring to. Very good. Very good. That is the thing I'm talking about. So practically speaking, if you're wondering what's going on with all this, I want to kind of reveal this to you. If you want to think about this from a C++ standpoint, you can imagine you have your header file. So you have a header file here. And this is your abstract class that's being described here. So this has all of those specifications of all of your member functions or methods, and also it could have all the attributes. So this is your abstract class here. And here's the perk about this, is if ever I want to implement the abstract data type, which is specified by this interface, in C++ this would be the abstract class, all I have to do is implement all of its member functions or methods. I'll usually use those terms synonymously. I know some C++ purists will be like, Dan, don't say that. That's like a Java thing. Don't worry. I understand that delineation, but most certainly for us, it won't make much of a difference. But anyways, here's the perk about this. You know that this is a header file, right? So you can always include this in a CPP file, and you can create and implement all of the methods of the given class, right? But with the thing you do is you need to inherit this, you have to make a subclass, right? So you make a subclass of the abstract class, and then you can implement all of the methods of that given class. And that's actually how, functionally speaking, you could do with C++. But here's the interesting thing. So you could think of the header file like the specification, just like the ADT. So from a software standpoint, you can imagine this like I have my specification, and now I want to actually implement it. So you would have naturally a CPP file that you can have. So you have your CPP file that has a class. So this would technically be a subclass. So it will inherit this abstract class. But the thing is, it's an abstract class, and the main reason why we don't have like a CPP file for this, keep in mind, you could always have one if you like. I'm just keeping it simple here. If you wanted to have an implemented, all you do is you just take this and you inherit it, right? You make a subclass. And here's the neat perk about this, and this has a natural analog to what I just described here. So, and you know about how, okay, if I have inheritance, if I have a subclass, technically that is of the type of its superclass, right? So if I have a class and its subclass, this is class A, that's class B. Class B is a subclass of class A. That means that anything that's B is also an A, right? So it's the exact same idea, just playing out right here. So if I implement the ADT, the abstract class, then I could call my thing that type. Is that neat? So that has a very natural theoretical and practical implication. That means that I can have, say, some class that implements this, but keep in mind, I can have many other ways of implementing my ADT, right? So that means that there could exist multiple other ways to implement the abstract data type. And each one of these would be a data structure. So the natural question in this course when we study data structures is which ones are the best ones, and we're going to see that sometimes that question is not as cut and dry. Sometimes there's trade-offs between different representations for the abstract data type when we actually implement it as a data structure. So the implementation of the abstract data type is the data structure. So data structure is a broader used term, but it's also a way of me saying, hey, look, I'm actually going to represent and implement all of these operations. And that's what a data structure is. So are there any questions about that? So I'm going to give you, after anybody has any other questions, I'll give you a working definition for us for a data structure, and then we'll start seeing some examples. So just remember, the whole idea with the interface is it tells me what it is. It doesn't tell me how it's done. So remember, this abstract class, this is my interface. So this is just what it would look like in C++. This is at least one way you could represent it in C++. Different programming languages will have a literal way of actually implementing an interface. Other ones won't. But either way, this is just an idea. Just keep in mind that this is just still a concept. So you don't have to adhere to the strictest rules of that language. These are just features that the language has. But no, if we're okay with this, give me 2 thumbs up. Okay, no, wonderful. So let me give you a working definition here for a data structure. So you're going to see it's going to look almost identical to the one I gave you the other day for an abstract data type. It's just that one part about the interface part is just going to be gone. So that's the plain way of me describing to you what a data structure is. So you're going to find that in this course, when we talk about abstract data types, what will happen is I'll pose it to you like it's a set of problems. And that's what makes it fascinating from a computer science standpoint. So a data structure is just simply a collection of values and objects. In fact, for dramatic purposes, I'll read this, although it looks nearly identical to the one I gave you the other day, with the exception of the one thing we just added here. It's a collection of values and objects and a set of operations on those values and objects, i.e., so notice it doesn't have the part about the interface. So this is actually a concrete representation of the abstract data type, its implementation. So this is a pretty broad definition. So some examples of data structures you're familiar with are things like arrays, linked lists, strings. Technically speaking, you'll notice that if I have a concrete representation of a stack is also a data structure, right? So keep in mind that this definition is rather encompassing. It's not like there's like a really like a blurred line that kind of says, hey, look, it's not this one thing versus this other thing. The thing that makes an abstract data type specifically is that it is only accessible through a public interface. The interface part's an important part of that definition. But now, the game in town is, I imagine I give you an ADT. I want to have it so I can represent the ADT by implementing it. So the idea is, if I want to take a stack, if I want to have the stack data structure, then all I have to do is know how to perform each one of the operations. And this is given actually by an algorithm. So each operation is actually going to be an algorithm. So we'll talk more about algorithms today and in its relation to problems in a little bit and how that data is organized. So these two things, addressing these two things, is going to be key to actually having a stack data structure. So just I want to remind you, just what I mentioned just earlier, functionally speaking, in C++, we say a class implements an interface that defines the ADT if it includes all the member functions or methods. Remember, I'm going to use these as synonyms, but I know purists will say Dan, you should only call it a member function. In its interface, each function is, sorry, I'm getting really excited here. Each function in its body correctly is implementing each method. So notice that there's actually a lot of loaded language in here. Technically speaking, I haven't told you what correctly implementing actually means, at least in this context. I'm just presuming you have an intuition of what that means. But so I want to show you that there's kind of like a practical software way of looking at it, but there's also this abstract idea way of looking at it. And the idea will be that now in this course, I could give you one of these ADTs. Now, from a practical level, what could happen is some user, say a customer, for example, gives you a bunch of specs they want. Then you'd formalize these into a set of requirements. Then what happens is you can take those requirements and you can encode these as functional needs or requirements. And each one of those can be described, for example, as a set, like an ADT, for example. But the thing that makes the ADT very fascinating is that you can just study an ADT just purely on its own regard. And you can talk about data structures and which ones are the most efficient ones for certain applications versus other ones, or just generally in the most pure way, in a computer science kind of way. You could do this, most certainly. And the thing is, now we're working at a level where we don't have to worry about those fuzzier details. Now we have an exact way of talking about, okay, here's an ADT. And in this course, you're going to find when we study data structures, we're going to talk about a lot of very commonly studied abstract data types. So as soon as you understand that all I'm doing is I give you a set of problems almost, that really all we're doing is studying how we can efficiently represent the data structure and how we could solve that problem, which the problem is given as a description as the abstract data type. So hopefully you find this fascinating that I've kind of just separated out a few different things. So now I don't have to talk about software, for example, really at all, which makes it very fascinating. But definitely those are things to consider on a practical level. But you're going to find in this course, we're going to see some things that are practically leaning, some that are going to be theory leaning, but both of these things often get married together in a course like this, where you're going to find that a lot of things that somebody might practically tell you might marry itself nicely to something you might see and will actually prove in class. So this is actually a nice feature of doing things this way. So that being said, I wanted to actually, like, let's take a stab at trying to make a stack data structure that only focuses on those two operations. So we'll see this representation later on in the course, but does everybody understand the game plan? So the game plan will be, especially when we start studying data structures, I'm going to give you an abstract data type, I'll tell you its operations, and then we'll study different ways we can actually represent it and implement all of its functions or methods. So we'll be describing those as algorithms. And I haven't told you what an algorithm is really yet. We're working our way there. So let's proceed. So let's talk a little bit about how we could actually take a stack and represent it and implement all of its operations. So remember, we have push and pop. So like I said, there can be other operations as well. So let's talk about how we could represent. Now there's several different data structures that you can have. They're all stacks. So you can have different kinds of stack data structures. We're going to study more of these later on in the course, but I will show you one, and I think this is a nice way of recapping something you may have seen in 115, or at least I hope you've seen, or linked lists. So has anybody never heard or seen a linked list before? Just want to make sure. If not, I could go a little bit slower with it. I know that you may have seen it a bit more lightly, or you maybe went all into it. Okay, so let's talk a little bit about how we can represent a stack using a linked list. So let's consider a stack implemented with a linked list. So I'll just remind you of a couple of things about linked lists. So one thing I should point out is that very often we'll describe this as a linked list-based implementation of a stack. Which, as I said, yeah, sure. Yeah, no worries. I will be walking you through kind of the structure of a linked list and remind you of a couple of key things that you should be aware of when it comes to the linked list. We'll definitely get a lot more exposure to these things, especially when it comes to the coding on the assignments. Anyways, remember my idea? I had like these plates. I had these plates, right? And I imagined them all as elements. Now, I'm going to strip away the idea that they're plates completely. So I want to imagine, like I had with my example at the beginning, I want to imagine like I just had the most simplistic way of representing this. So instead of thinking of plates, I imagine the stack more like this. So instead of having plates, I'm just going to imagine I have a stack that's red, like this, where that's the top of the stack. So remember that a stack, this is the top. The operations don't have access to the bottom of the stack, for example. It's always the top. What I would like to do is I would like to have a natural way of representing this so that one is fast to perform these two operations, but at the same time, it also is conceptually simple for us, at least at this stage. So I want to remind you about a linked list. So let's talk a little bit about a linked list first, and then I'm going to try to specialize it for the stack. How does that sound, everybody? So I want to remind you that we have, in a linked list, we have these things we call nodes, right? So we have a node. So this is a node here. And linked lists, each one of the nodes will have typically a data attribute. And it has a next attribute, which is a pointer or reference to the next node. So for example, so each one of our nodes is structured like this. So this could be like a number in here. It could be some element. So I'm not going to be focused so much on the types of data that are in there for the data attribute. It's not really that important for us at this stage. So for example, I could have the data being the letter A, for example, or the letter B, or the C, or the D I have over here. But the point is if I have another node, I'll put as the next attribute here to be a pointer. It's going to point at the next node in the linked list. But the big attribute we have with our linked list is the head of the linked list. The head of the linked list will point at the first node in the linked list. So, for example, if I wanted to have a linked list where I have attributes, where I have my elements like A and B like this, I might have it where I have one node that has A in it. The next attribute will point to the node that has as its data attribute B, and its next attribute, in this case, suppose that there is nothing after. We would just have null pointer as its next attribute, or nil, or null. So does this give you a warm-up or remind you about linked lists? So remember that it consists of nodes, and we have a head of the linked list that points at the first node. And the idea is that unlike an array, this is not contiguous in memory, meaning that the places that these nodes could be in memory aren't necessarily right beside each other like in an array. There's pros and cons to this. So for example, like in an array, you can actually directly access any one of the positions in the array, right? You have instantaneous access or random access to each position in the array. In a linked list, what do you have to do instead? So I would start off at the head, right? I would maybe assign a variable, maybe call it like cur. And I would be like a pointer to some node. I'll make it whatever head is. Whatever head is, I'll copy that. And that'll be to the head, whatever the first node is. So what would I do to go through this linked list? Any ideas? So what do I have to do? I would use a loop, for example. I could use a while loop. For example, I could check if cur is not equal to null pointer, right? Or null, or nil. Right, I could use a loop. and I could just simply reassign cur to be whatever the next attribute is in that node, right? So I'm sure you've probably seen this in 115 before, at least some element of this idea. The idea is that to traverse through the linked list, I have to follow the next attribute of each one of the nodes until I reach the end. So that's how we would normally traverse through a linked list, right? And naturally, when you want to insert and remove, you have to find the appropriate node, and then you would have to do a little bit of surgery on the pointer to whether you need to put a node in here or you're going to be removing a node. Make sure you hang on carefully to what pointer you have so you can point at the appropriate node, whether it be, if it's a removal, I would remove, say, this node. In this case, you would make just this null, but that would just simply be the next attribute of this node, right? But anyways, hopefully this gives you a little bit of a reminder about linked lists. So now let's talk about the stack. Now, it's very easy for me to imagine it just like a stack of plates like this. But here's another way. Imagine you take what I just drew over here, you tilt it sideways like this, but you read off the elements from left to right. So you have A, B, C, D. Now you could probably see a very natural way you could do this with an array, right? We'll talk more about that later on in the course, but I want to show you how you could do with a linked list. Well, you could do the same exact idea. Now, the difference is I'm going to imagine I have each one of my plates. So this is the top of the stack. I'm going to put it right here. Then I would have the next one after that. Then I have the next one after that. Then I would have the next one after that, and so on. So remember, the top of the stack was the blue one, right? So imagine this. Imagine I have each one of my elements. What if I were to just put that inside of a node? So I just make that the data attribute of a node. Now, the great thing is that the top of the stack is actually, it's literally, it'll contain the element of the first node in the linked list. So putting this all together, a very natural way to me represent this is, instead of imagining head, just as just a generic head of a linked list, consider this the top of the stack. So there's the top of the stack right here. So I'm just going to call it top. So the top of the stack, just like in my picture here, notice that it's pointing at the top element. But now I have a node here. And if I get the data of this node, I can get the top element. Do you ever see that? So likewise, I can work just like I have my plates. I laid them out like this. I could do the same thing with the linked list, where each one of these is in a node. So I could just have A, B, C, D, like this. So you see how I can represent the data using a linked list. It's very natural. But there's a very big perk about doing this. Do you notice that the top of the stack is always the first node? Now, is there something that you know about linked lists there's something interesting about our stack. Everything we did and talked about with the stack always involved the top of the stack, right? Always involved the top of the stack. So what manipulations need to happen with our linked list? Are they going to happen over here in the linked list, or are they going to happen always over here? Always at the top, right? That makes it very easy to implement, because that happens to also be one of the simplest cases for insertion and removal in a linked list, right? So let's talk about how we could do push and pop now. So let's see what we could do with push and pop. So let's talk about push. So I'm going to describe it in words, but I must stress that you can easily describe this as a computer program, as a function, or as what we're going to call pseudocode, as an algorithm. A lot of these are all different manifestations of an algorithm. So I can describe it in words to you. I can give you what we're going to call pseudocode. We can also describe it as an actual function like C++. But I'll just describe it in words for the sake of brevity for us. So the push is just like doing an insertion of a new data item that I want to put into the linked list. So first of all, I'm going to do is I'm going to create a new node. So I'm going to create a node containing E as its data, and insert it at the front of the linked list. At the front, if you prefer to call it the head, be my guest. I'm just going to call it the front just to keep things conceptually simple. At the front of the linked list. So notice that this is just a description of an algorithm, right? I would create the node, then I just insert it at the front of the linked list. But you know how to do this, right? You know how to insert into a linked list. You know that you just have to traverse to the appropriate spot, you put it in. But here's the thing, it's always at the front, right? So here's the thing, if I wanted to do a push operation, say for example, I need to push F. Well, all I would do is I'd just create a new node, I'd put F in as its data, and then I would just reassign the appropriate attributes. So for example, I know top currently is pointing at A, I would make whatever top is be the next attribute, and then I would update top to just be that, right? It's a piece of cake. So that's how I could just do my push operation. Isn't that nice and straightforward? So I have a question for you. Given sufficient time, could you take this description and write it into C++ code? Yeah, right? See, that's the great thing about this, is that notice that like it didn't matter, like you understand the ideas, but I don't have to tell it to you in C++. I could tell, like what I described to you is equally as applicable if I gave you Java, for example, or whatever language that supports a lot of the features that we're used to. So let's talk about pop. Okay, let's talk about pop. Pop is also as well. Let's talk about pop. Naturally, we just simply remove the first node. First node in the linked list. And return its data, right? So you just take and you're just going to return the data. Now, I must stress that if there are no nodes in our linked list, which you can actually access very easily if you have a size attribute. So if you have a linked list, you keep track of the size of the linked list, as in the number of nodes it has. Then it's really easy to check if there's no nodes. So I want to make a caveat that if there are, and return null if there are no nodes. Right? So, like I said, notice that I've given you a way of representing the data. I've also given you algorithms, just these are written in words. But the thing is, I'm relying on your understanding to understand these two algorithms, right? Because I know that you know a little bit about linked lists. So are there any questions about this? Any questions at all? So notice that I've now described to you something. So if I gave you this linked list and I also introduced these other operations, I can call that a stack. But I must stress that you have to be very careful because when it comes to general concepts like this, remember, I'm just describing an algorithm to you. So remember that sometimes the big obstacle when you're working on the assignment is figuring out some of these details. So you can always discuss these things with classmates, but most certainly I would not recommend just spelling out this to a student. Just talk about it. You have a discussion, of course, but make it so that it's something that you could talk about it amongst each other. I wouldn't recommend just spilling out the entire algorithm to somebody. But most certainly, when it comes to academic integrity, I must stress that if this was a programming assignment, this won't help you, right? You still have to implement it. Yeah, no worries. No, thank you for the question. Okay, so we talked about how we can represent a stack. Let's move on to another concept. So I thought it would give us a little bit of a basic startup with data structures so that when we revisit data structures later, you understand the game. The game is I give you an ADT. The goal is to implement it, get a data structure. And we'll talk about different ways we can implement these ADTs as data structures. And we'll see all about interesting phenomenon. For example, there's sometimes trade-offs that occur. Sometimes some operations perform much faster than other ones. And this is by the design of how the data is represented. So sometimes we're going to be addressing how we can speed up the operations by introducing new ideas that maybe you didn't see in 115. So let's talk about something else. So you're going to see that this is one piece of the puzzle in this course. I want to talk about the next piece. So you know how I talked about how a data structure can be, an ADT, the specifications, can be viewed like a problem. So like it's just like a set of problems where the question is, okay, what's the fastest way you can implement one of these operations, like the push or the pop? You could view these like algorithms problems. So like I want to say, hey, look, here's my operation. Can you make a faster algorithm for implementing that operation? Now, a data structure is a little bit more complex than just that because you have to take everything together. So I thought I would start off with something a little bit more, I don't know, fundamental. So let's talk about problems. You're going to find that there's an appreciation that we can have for talking about concepts in a much more exact way. Why? Because intrinsically, being able to exactly specify things helps make things easier for us to communicate with other people. But at the same time, by formulating it in an exact way, it gives us the perk that since it's exactly specified, it also is completely and capable of being studied in the way using the mayonnaise or mustard. The dreaded mayonnaise. So I must stress that problems are all around us just waiting to be solved, right? But I must stress that we're going to focus and limit ourselves to problems that are of a specific form in this course. So there's a lot of different kinds of problems out there that are studied in computer science. I'm going to keep it kind of basic. And as you progress through your studies, you're going to see a whole bunch of different kinds of problems. So you're going to encounter many kinds of different problems. So I'll say you will encounter many different kinds of problems in your studies. So I thought and I must stress that a lot of these are fundamental or very basic problems. So I thought I would give you one example. So I'm going to describe something called the search problem. It's a rather broad class of problems, but for us, we'll keep it really straightforward. So the search problem, I could describe it to you like this, and you'll notice that the way I formulate problems to you is a very common way in computer science, is that I give you input. So imagine I give you some input. I expect it to do something as output. So you're going to find that the way I want you to observe this structure every time I formulate a problem to you. You're going to see that that's going to be a common occurrence throughout this entire course. So imagine I given a set S. So just think of this as just a collection of elements. A set S of elements, and an element X. And an element X. Determine whether X is in S. That's a basic formulation of the search problem. So I give you a bunch of elements that might be I must stress that the set might be represented in a variety of different ways. We're going to focus primarily on when S is an array. And we'll determine, okay, if I give you this set S, so an array, and I give you an element X, you can think of this like a key. So I give you these two things as input. I want to know, true or false, whether x is in S or not. So keep in mind that there's a lot of different ways I could reformulate this to solve this specific problem, but most certainly we'll see a couple different ways I can do that. So notice that the input here would be the set S, and I'll have an element X. And as my solution, what I want as my solution is to know if X is an S, right? So just keep an eye out for this kind of pattern as we explore things in this course. So I must stress that usually with this problem, S is typically assumed to be large. Why? Now, in everyday life, when people like you and me, everybody, when we're dealing with daily tasks, we're very used to the idea we have dozens of tasks that we need to do. Now, in the sense of computation, that doesn't necessarily have to only be dozens. It could be hundreds, thousands, even millions, even more. It might be hundreds of millions. So the context of large depends largely on the context for the application. So you're going to find that some of the things you maybe done earlier courses, some of the sizes of how big, like how many inputs or how many possible data elements you might have, may not have been as large. You're going to find that as we explore things in this course, you're going to find that a lot of the techniques are going to lend themselves much more to when the data sets are something like at least in the thousands to tens of thousands to hundreds of thousands to millions. So I'm hoping that you have an appreciation for the contextual use of the word large. So I'm going to put that in quotes. So I want to give you a few applications of this problem just so that you understand that some people just don't study problems just out of the ether, right? These things are things that actually people are interested in. Very often when you study different computational problems, there's often a very natural analog to something in the real world, or there's a problem of interest that needs to be solved. Sometimes problems are just studied for purely computer science related research reasons. There's some people that spend their whole career just studying very abstract computational problems, but they have very fundamental implications for other things. So don't just presume that it has to be practical. It most certainly doesn't have to be. But it definitely is something, it makes a lot more sense when you study a problem and actually has something that has something to do with things that people can easily relate to. But most certainly, it doesn't have to be. This one's an example of one that does. So here's some example applications. Just to give you a flavor for what the search problem really means. So imagine I gave you S. You could think of S as the variables in a program. So I can think of that as S and a name of a variable. So suppose I have a program and I want to find a given variable in that computer program. This is one way I can cast the input as something that is very real. I give you a program and I want to know where that variable occurs in the program. So you can think of it like a search feature. Imagine I have student records. So you can imagine I have a whole bunch of student records. You can think of that as S. And a student ID, which you can think of that as X. Likewise, you can even think of things more, maybe an online application. For example, you can think of a web host name or web host names. Which you can think of that as S. And a URL, which you can think of that as X. So, like I said, there's numerous applications for the search problem. This is why I usually like to start off with this one. It's because it's something that's very easy to relate to. But there's a lot of other kinds of problems you've actually encountered before. For example, sorting. Sorting is something that you studied a little bit in 115. We're going to see more sorting in this course, but that's also a problem. So let me give you a kind of a working definition for what a problem is, and I'll draw a fun picture to accompany it. So let's head over here. So just keep in the back of your mind that there's this thing that we have where we have some input and we have some desired solution. But notice that every time I gave you one of these examples over here, I always told you what the inputs represented, right? But really, when we think about the problem, you can think of any set S and any, I guess you can think of it like the key or element. I have X. As long as I'm given those two, that gives you what we're going to call an instance of a problem. So let's talk. I'm just going to give you this fun definition for a problem. I'll let you think about it. So I'm going to start off with the most cop-out way of giving you a definition, and then I'll give you something a little bit more formal. So a question or statement that requires solving. See, that's my cop-out definition. Requires solving. This is the one that you give people when they don't really like, okay, well, what is a problem? That's like your overarching definition. When somebody talks to somebody in normal life, you're like, hey, what's a problem? Usually problems are things that are usually described as something that you want to try to solve. Now, a computational problem, which I'll colloquially always refer to as a problem, which in the sense when you study things in computer science, that's what we usually talk about as a problem, a computational problem. And I must stress that as you study different kinds of problems, this definition will slightly deviate or even might generalize even further. A computational problem is a, or n, at least the ones that are interesting for us, is an infinite collection. But if you don't want the infinite part, it's just a collection. It can be finite or infinite. But for our problems that we're interested in, normally it's infinite. An infinite collection of possible problem instances. Of possible problem instances. Problem instances. So you think of it like a big collection, just a big bucket. A bucket that is like infinitely deep, full of these things I call problem instances. So I've got to tell you what a problem instance is, or what I'll just refer to as an instance. Each problem instance, or just instance, which I'll just usually use, each instance has inputs, potentially one or more, which if ever I need to specifically talk about that and to delineate between its solution, I'll usually refer to this as the input instance. And upon being solved, has a solution. So I'll just presume that it has a solution. So it has inputs. So what the definition of an instance is just a collection of inputs. And the thing is, it'll become very natural in a course such as like CS210, is that you can imagine these inputs like they're actual machine code on a computer that's represented in binary, which will come very closely related to something I'll say in a moment. So you might look at this like, damn, what the heck does that mean? So let me give you a fun picture to just really kind of hammer in where I'm going with this. So imagine this is my problem. And I have a whole bunch of these so-called problem instances. I have a whole bunch in here. Each one of these is a problem instance. So I have a question for you. Suppose that I wanted to develop a computer program. And that computer program, suppose it's sufficiently capable of reading the inputs. So imagine it's like a function that takes the inputs of a given problem. So in our case, like the search problem takes the set S, which in our case will be an array, and an element X. And it's supposed to tell you if X is in that set or not. You can imagine each one of these as a pair, a set S with a key X. Each one of these dots is one of those. And each one has an answer, either true or false. Either it's in it or it isn't. So I have a question for you. In fact, it's more of just a discussion point. If I wanted to know if I've solved a problem or not, does anybody have any ideas of how I might try to formulate that idea? So imagine I give you a problem, and it's described like this. There's all these problem instances. What should the algorithm or computer program be capable of doing? So it takes it, and it takes in a problem instance. And what does it have to always do? Yeah, it has to give you the solution, right? Each one of these has a solution. Exactly, both of you got it right. So notice that it has to be the case that no matter which dot I pick out of here, it always has to give me the solution to that problem instance. Very good, very good. So you're going to see that that's exactly how I'm going to define correctness when we talk about an algorithm later. So you're going to see that really all these dots, each one of these, I'll give you a concrete example of what I mean by this picture here in a moment. So I thought a good way of describing this to you is with sorting. So you've seen sorting before. We'll see more sorting in this course too. So sorting. So here's a problem called sorting. So imagine I'm given an array A and just to make it simpler for us to discuss this, because keep in mind I can make sorting a much more general problem. Technically, you could call this integer sorting. I'll say of n integers. So imagine I'm giving you an array of n integers. I want to sort A in non-decreasing order. So for those that are not acquainted, the term non-decreasing, you may have seen it before. It just simply means smallest to largest. This is just smallest to largest. The reason why it's non-decreasing as opposed to increasing is because some of the elements might be equal to each other. So this is the problem I know you've encountered before. So for example, I can give you a whole bunch of different problem instances. So here's some examples of problem instances for this. So for example, I could give you A, and suppose I give you an array that says has 5 elements, 1, 2, 1, 3, 5. Can somebody tell me the solution to this problem instance? So one of these dots is this, if I think about the sorting problem. So imagine I have the sorting problem. Each one of these dots is going to be an array of length n, where n is going to be fixed for that one instance. So can somebody tell me what would be the solution to this array here? So what would be the solution for this? So if I'm considering sorting, which says I've given this array A, I want to sort A in non-decreasing order. Yeah, there it is. There it goes. 1, 1, 2, 3, 5, right? Very good. So notice that so the way I've defined the problem, every one of them has a solution. In this case, I just give you it in sorted order, right? Very good. Very good. So here's another instance. Here's another instance. So I have A. Suppose I give you 1, 1. Let's go 1, 1, 8, 6, 7. Somebody tell me the solution to this instance. What's the solution to this instance? It's 1, 1, 8, 6, 7. Yeah. Yep, very good. So notice that you just have to put these two before the 8. Very good, very good. So notice that all of these are arrays of length 5, but I must stress that this sorting problem actually consists of all possible arrays of length n, where I go over all possible integers that are positive. So it means that in this bubble here, you're going to have those two instances will be in here. These will be 2 dots in here. but also there'll be an array of length 100 that has 100 integers in it. There'll be another dot that has 10,000 integers inside of it. There's another one that might only have one integer in it. The point is it's going to consist of all possible arrays of a given length. But they're all of these. So what does that mean for when we talk about solving a problem? To exactly solve a problem requires solving every problem instance. So you're going to see that there's something very fascinating about this as a consequence. So if I give you a problem that's described just like my sorting problem, could I just like make a computer program that can go through every single possible array? Like say I propose to you, say, hey guys, I came up with a new sorting algorithm. Here's an implemented in C++. Like, could you write up like a computer program that can conceivably go through every single problem instance in finite time? Is it possible? So far I'm getting one yes. So keep in mind, the question I'm asking is, could you, if I gave you an algorithm that's implemented in C++, I wanted to check it. And keep in mind, remember, this consists of all possible arrays of length n, every single one. It means there's an array for each given integer, and there's infinitely many of these. Yeah, so I'm seeing a lot of no's. Does anybody want to give me a reason why? Maybe the answer might be no. Any ideas at all? Yes, so notice that I have infinitely many things to check, right? Now, in only very specialized situations could I carve out this and try to reduce it down to a subset that might have very simple ways of checking them. But generally here, there's no such, well, I'm not aware of any such structure that's possible here. But most certainly that's me just giving you my ignorance, but most certainly more generally, if somebody proposed this exercise to you, you most certainly generally could not do such a thing, right? This is why we're going to need sometimes that lovely tool, that mayonnaise for our sandwich. We're going to sometimes need to pull that out. So I'm hoping that this convinces you that if we're solving a problem like this, and we want to make sure that the algorithm, or if we implement it, its implementation, like say in C++, assuming it's done correctly, I want to ensure that it always works. Now, this is a very different question than, say, I'm just testing it to work for very specific circumstances. That's a different question. Here we care about it being correct in the most purest way possible. And that's the best way, by the way. So hopefully you found this kind of fascinating here. So now that we've laid out the idea of a problem, you notice I talked about these problem instances, each one of these dots. I would like to have some way to measure how efficiently one program is versus another. Or in this course, we're going to focus mostly on the more mayonnaise and mustard side, the algorithms. I want to know, how can I measure how efficient an algorithm is? And typically in computer science, the most classic way of doing this is by measuring it based on the size of the problem instance. So the size of the inputs. So this is what we refer to as input size. So I want to talk a little bit about that so you can get an idea, or at least a grip on this idea. Because at first it seems a little bit strange. Why would you be measuring it by the input size? Like what does that mean? Like what is that? So let's talk about this. So you're going to find that when we measure the efficiency or running time of computer programs or algorithms, we normally need some measurement, some bar-based measurement to say, okay, as the computer program does something, I need some way of measuring faster versus slower, but most certainly I need some base measurement. Now, one natural phenomenon that happens with most algorithms, in fact, in many computational settings, regardless if we're talking about the mayonnaise and mustard, to an actual killer application, is the idea that as the input gets bigger, as I give you longer and longer arrays, should the program take longer or shorter? Like say if I'm thinking about the sorting problem. Would it make sense that the longest it possibly can take for a given problem instance of a given size, if I make that longer, if I make the size of the input bigger, the program problem will take longer, right? So this is where the intuition behind, at least this is one intuition behind input size. So let's talk about input size. Now, I've included a few more details in the notes if you really want to kind of dive a little bit further in to this topic, because I could really slice and dice this topic for you. But for this course, we only need to kind of have a basic understanding of input size. So each problem defines a problem instance. Defines a problem instance, each with its own size. So I just want to kind of recap a few things. Each with its own size. So more formally, so here's the kind of formal definition in a more formal direction. Formally, input size is determined by how many bits, and I must stress that when I use the word bits, I'm not trying to be specific just only to binary. My apologies. It's not just that you need, it requires that it's bits. Any other reasonable encoding scheme? My apologies. I apologize to headphone users there. That was pretty bad. Is that, for example, ternary, that's okay. Base 4 is okay. Base 16 is okay. Just gonna drink some water here. The bad one is unary. My apologies. So how many bits required to encode it? As I said, typically the larger the input is, the longer a program will take, or the longer the algorithm takes to run in the worst case, which I'm going to define in upcoming lectures. I promise you I'm not dying right now. So, anyways, I have a very interesting question to you. Does anybody remember how many bits, say, something like an integer has? Like just like type int. There was a bunch. I'm so sorry about that. The point is that it's some constant number of bits that are used to represent type int, right? So in this course, I will typically assume that the numbers are always encoded using a fixed number of bits. So for example, when I have my array over there, notice that each one of the numbers in the array, you can think of this as an array of ints. But keep in mind that theoretically speaking, it can be any constant number of bits that are used. So, that being sort of said, you're going to find that when we want to measure the input size, we can take some reasonable considerations when we actually do this. So, one technical thing I need to make a remark about is that if you don't know that the numbers are always going to be of a fixed number of bits in terms of their size, you have to be a bit careful, but we're going to always presume that our computer is capable of always reading the input. I'll talk more about that as we go along. So if you assume that the sizes or the number of bits used to represent the numbers, or naturally, any other data type that can be coded as bits, which also is a number, if you think of it like that. Each one of these also is some fixed number of bits. So when we measure the input size, especially in this course, unless we specifically run into a running time that involves numbers that pop up from the input, which we will not run into in this course, that'll be something more that we might see in something like 340. The only time that we have to really worry about, well, really the main thing we have to worry about is actually the number of items. Because if you think about it, if I give you, say, an array of length 16, and each one is an int, notice it's just 16 times the number of ints in terms of the size, right? So notice I give you an arbitrary length n. Notice that it's just some constant times n, right? So we care about the n, not necessarily about the constants. You're going to see as we're going to go along, we're going to talk about something called big O notation. And we're going to see that these constants don't really matter much. At least when it comes to kind of fundamental ideas like this, but only in very narrow applications will it will. So I want to give you some examples. So imagine I'm considering the sorting problem again. So suppose I want to sort an array of length n. I'm just going to start off with this. The input size, so a reasonable way of considering the input size here would just make it consider it as n. Why? Because each one of my numbers is some constant number of bits, so I don't really care about so much that attribute to it. It's more about how many numbers there are. In this case, there's n of them, right? Now, for those that have studied a little bit of linear algebra, you may or may not have. You're absolutely not required to be in this course at all. But suppose you wanted to multiply two matrices. The input size here, does anybody have any ideas what the input size would be? Imagine I give you, say, a matrix I would like to multiply with another matrix. What would be the input size here? Any ideas? Just think about it, instead of thinking of it just like an array, think of it like a two-dimensional array. Yeah, if it was a square matrix, it would just be n by n. But this is really just the dimensions of the matrices, right? So, very good, very good. As input size of the dimension of matrices. So it's just going to be the dimensions of the matrices, because each one will just have a number. And if we assume that each one's encoded with a finite number of bits, that's some fixed number, this is another way I could consider that. Now, if you ever need to get more specific and consider the input size more carefully, one natural application or place that you have to be a bit more careful is in number theoretic settings. Sometimes you run into problems that involve numbers. They don't necessarily have to be from number theory. For example, some problems that are optimization, they sometimes have numbers in the input that sometimes creep up in the running times. That's when sometimes you have to be a bit careful about how you measure the input size. So determining if a number is prime. Now I must stress that in this problem, I'm given an integer, and I would like to know if it's prime or not. Now, if you think about it, in all of these settings, it was okay for us to just presume that the integer always was a fixed number of bits. Now, in our algorithms, we can always presume that the computer is capable of reading the input. So it's an okay assumption there. It all works for these first two. But sometimes you have to be a bit more careful about the running time. This is one of these cases. So if you take a look at my original picture here, this one over here, each one of these dots would just be a different integer. And I would like to know if each one is prime or not. So in this specific circumstance, what would be a more reasonable way of considering the input size here? Any ideas? So should I stick to this, like counting up the number of items that are in it? Or should I use the formal definition up here? And remember, for us in matter of study, we always have to just, as long as we make a reasonable consideration of the input size, we're okay. So it doesn't have to be the exact measurement of it, but you have to be careful because sometimes when we study some algorithms, sometimes the running time actually has an influence based on the input, but not in a way that we would expect. It might actually be literally the numbers themselves, which this is something we won't run into so much in this course, but sometimes if I teach like 340, for example, I sometimes show an example where this manifests. But I'll tell you. So in this case, if I wanted to test if a number is prime, it may have input size of the number of bits required to represent the number. So the one thing I'll tell you up front is we're going to only care about these two examples in this course. We will not run into phenomena like this, but I must stress that you can take this formal definition and apply it to everything that we're doing. But what we're going to care about is really the number of items that are in the input and presume that each one of the items is encoded with a fixed number of bits. Okay, so as soon as you just understand this first example primarily, you're pretty much in good shape. So are there any questions about input size? Because I'm going to show you one last thing and then we'll leave things for today. Because I want to put all the pieces we talked about here together with the notion of what an algorithm is. Then we'll come back next time to talk a bit more about what an algorithm is. Okay. So I'm going to draw you a fun picture now, and I think this is the perfect way for me to end the lecture so that we can come back and talk more about algorithms. So I'm going to draw you a fun picture. I find that this helps students really kind of see the connection between all the things we've just talked about here. So remember, I have my problem, I have problem instances, and right now you sort of have an idea of what an algorithm is, right? You can think of it just like a computer program. So here's going to be kind of like the big idea. Just to summarize what we talked about earlier. So here's the big idea. So you have your problem instances, each one of those little dots, right? Each one of those, my apologies, I'm really sorry about that. Each one of these is a problem instance. Each problem instance consists of its input. So this would be the input. So what I refer to as the input instance sometimes. So the inputs. So I have my problem instance that has input, which that's what dictates what the instance is. Each one has a solution. Right? That's what we talked about. Now, what we're going to see next class is that when we talk about an algorithm, just like what you think about when you talk about like a function, you can imagine this input is given as input to the algorithm. So it's given to the algorithm. Then, you know, an algorithm will produce output sometimes, especially if we're talking about a problem that has have output dictated for it. It does some processing. It produces output, and the natural question is to know if this is correct or not. So we're going to look more about that at next class, okay? So that being said, when we come back next time, we'll talk more about algorithms, and we'll see more about this thing we called a little bit earlier about pseudocode. We'll talk more about that next time. So I'll say thank you very much, and have yourself a beautiful day. I'll see you tomorrow.